Hey, good morning, guys. How you doing? So I am ever so sorry I haven't been in so far this week. You need to know that I truly hate not being here. I was hoping to be here, not have as many absences this year, but 2023 is kind of like the revenge of 2022 so far. So yeah, hopefully it'll get back to normal. Should be in on Thursday. I apologize. So here's what we're going to do. We're going to do the notes that I was going to do if I was in class. We're just going to do them online. And this is talking about something called the impulse momentum theorem. Okay, so impulse momentum theorem. What is the impulse momentum theorem? An impulse is, first of all, a new term. An impulse is something that gives an object momentum. It increases or decreases the momentum of an object. Now, the best example I can think of this, and I can't really show you because I'm not there, but I want you to imagine air hockey, the little puck, right? You got the little puck, it's sliding along the table. There's no forces acting on it in the sideways x direction. It's just moving. Object in motion stays in motion. It has momentum because it has mass. It has a velocity. It has momentum as it slowly slides from one side of the table to the other. But something had to give it that momentum. And let's be honest, it was you hitting it with that little white slider thing you hold in your hand, right? So let's just assume the puck wasn't moving. You got the little slider thing. You smacked it, and as you smacked it, the short, tenth of a second you were smacking it, you were applying a force over a very short amount of time. That gave it the momentum. That is what we call an impulse. And it can be derived from Newton's second law. I'll just show you where it comes from. Newton's second law is, of course, force equals mass times acceleration. We know that acceleration is the change in velocity over time. So all we're going to do is we're going to take this little time, we're going to multiply it to both sides, put it up here, and we have force times the change in time is equal to mass multiplied by the change in velocity. That is the impulse momentum theorem. It's kind of weird because this side of the equation, force times delta t, is what we call the impulse, and this mass times the change in velocity is equal to the change in momentum. So an impulse is a force acting over a time. Momentum is just mass times the change in velocity. Oftentimes you don't really change the mass of anything. It's constant. I mean, not always, but so the only way you can change an object's momentum is to change its velocity. So that's the impulse momentum theorem. Okay, so good news, chaps. This is pretty much it for the lesson, apart from the fact that I really want to make sure that we understand this. So I've got a few more things I want you to sketch down in your notebooks and then an exit slip. But this is it. So feel free to pause now, but I'm going to go on to some examples. And I'm going to go on to this one. Rock climbing. I didn't know this when I first went rock climbing with a friend of mine. And he told me that the rope has to be stretchy. So is it a good idea for rock climbers to have stretchy rope or not? Well, that's a tricky one, isn't it? Because you think, well, if it stretches, you're going to kind of like just keep going and hit the ground. But then you got to think, well, what wouldn't happen? I mean, if you look at this rock climber, what they're doing is they have these little bolts right there. They're connecting the rope in. So now if this person falls, they're only going to kind of swing this little distance because they're connected there. Very clever way of doing it, actually. So do you want a stretchy rope or an unstretchy rope? Well, you are going to want a stretchy rope, but why is that? Well, you know what? Let's just change the question and then come back to this. If you go bungee jumping, do you want a bungee cord that stretches or a bungee cord that doesn't stretch? And this is where it kind of makes sense. I'm going to go ahead and argue that you are going to want a bungee cord that stretches, because if you jump off a bridge or whatever it is, you're going pretty fast by the time you get to the end of that rope, right? You have a certain amount of momentum. You have your body mass and you are traveling a certain velocity, and you need to safely lose that momentum. If you had a rope that does not stretch, then the amount of time it's going to take to stop you is going to be really, 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 really small. If I have a really small delta t, that means I'm going to have a huge amount of force. This is me drawing out a force with my mouse, a huge amount of force in order to stop me in a very, very, very small amount of time. And that will probably result in me breaking my legs or having my legs ripped clean off my body. It's gruesome to think about. But if we have a nice stretchy rope, I don't know if you've seen videos of bungee jumpers, but by the time they get to the end of the rope, then they have to start slowing down. It takes, 3, 4, 5, 6 seconds for this bungee to stretch out and to slow you down, to arrest all of this velocity. If you have a nice big delta t, this is me writing out my big delta t, then the force is going to be nice and small, nice and manageable. So if you want to decrease the force in an impulse, you need to increase the amount of time that the impulse happens over. So again, I'm not talking about the time in the air or anything about that. I'm talking about the time from when the bungee first kind of gets tight to when you finally fully stretched and you've stopped. You want that to be as big as possible. If you want to go the other way, you want to make it as small as possible. So let me talk about hitting people. Don't encourage this, of course, but if you're Mr. Blue here, you're punching the red boxer. In theory, I know there's a lot of boxing that I don't fully understand, but in theory, do you want to punch through or jab back? Do you want to increase the amount of time your fist is in contact with this dude's chin, or do you want to decrease it? In theory, and again, there's a lot to boxing that I don't fully understand, you're going to want to get your fist to hit the dude's face and stop in the shortest amount of time possible in order to impart the maximum amount of force. Flip this on its head. If you're Mr. Red here, you're getting punched in the face. You're not very happy about it. What are you going to prefer? Are you going to prefer a short time or a long time? Well, the reality is you're going to want this dude's fist to be in contact with your face for as long as possible, because again, the fist has mass, the fist has a velocity, it has momentum. You need to get rid of that velocity as that momentum as his fist comes to a stop. You can either have a big force over a short amount of time, or you can have a small force, reduce the force of it hitting your chin over a big amount of time, over a big delta T. Now, if I increases the time, it decreases the force. So what this guy is going to do is he's going to roll his head back. You heard the term roll with the punches? He's going to basically move his head back to increase the amount of time it takes for this fist to come to a stop and decrease the force. All right, and that is pretty much it. I want to talk about one other thing, but I don't know if the video is the best way to do that. So I'm going to ask you this. Tank versus car, but you know what? It's not tank versus car because I'm pretty sure the tank will just go over the car. So I'm going to give you a hypothetical. You have a tank driving straight towards a cliff, a huge rock that just ain't going to move. The tank is solid metal, solid armor, and the tank ain't going to bend or buckle, versus the car's driving towards a cliff. The car hits a cliff, crumples up. Which one would you rather be in? The tank that doesn't bend or buckle at all, and obviously the cliff doesn't move, or the car that does bend or buckle, and obviously the cliff doesn't move? Which one would you rather be an occupant in? Because I know which one I would rather be an occupant in, and we'll talk about that on Thursday. So I'm going to ask you to answer that question as an exit slip question. Again, I just clicked off by accident. Look at this equation. F delta T equals M delta V. The question is, by the crumpling or not crumpling, do you want a big delta T or a small delta T? Which one will be better? It's kind of counterintuitive because I know my mother-in-law always talked about she wants a tank of a car because she'll feel safe. And I always felt that that was an interesting idea with the physics involved. So answer that question as your exit slip and we'll call it for today. All right, have a good day. Hopefully be back tomorrow. Right out.